So yesterday we were talking about, or in the last video, we were talking about weight equals mass times gravity. And we're going to do a little bit more with that today. So let's just remind ourselves weight is mg, and that's really just F equals ma, because the A is just the force of gravity. We don't even need to use weight. Some books prefer to use Fg. I'm going to use weight because I don't like all those little subscripts. Sometimes they're confusing. So we're going to have a 60 kilogram person. That's their mass. Mass never changes. They're 60 kilograms because of the amount of atoms they have in their body, the number of atoms they have in their body. And that doesn't change if they go to the moon. On the moon, they only weigh 100 newtons. So let's see what we know. Weight is mg, but it won't be 9.8 because they're on the moon. So we can rearrange that formula. I just divided both sides by m. And I know it's a slash there instead of a fraction. That's okay. And now the problem is really, really easy. We just divide the 100 newtons by the 60 kilograms, and we get 1.67 meters per second squared. And if you would do the math, if you would take 1.67 over 9.8, you get really, really close to 1/6. And that's the actual value. So however far you could jump on the Earth, you could jump about 6 times that on the moon because the pull of gravity is that much less. Or if you've seen videos where astronauts are bouncing around and they're kind of like hopping, almost like an Easter bunny or something, that's true. Because even though those spacesuits are so heavy, the pull of gravity is only 1/6. And that's why I said like they kind of hop around like a bunny. So let's do another problem here with weight and acceleration due to gravity, and then we'll move on to some different things. So the first one says, well, what's the weight of a 56 kilogram person? And that's just using mg. 56 kilograms times 9.8 meters per second squared, and we'll see what that works out to. That works out to a handsome 549 newtons. Now on the moon, it's still mg, but it's not the mass or the gravity for the Earth. It's what we saw in the last problem, 1.67 meters per second squared, and that works out to 93.5 newtons. So their weight is 1/6. Their mass hasn't changed. Now maybe these people are fortunate enough to go to another planet. Now on that planet, that person feels heavier. Their weight is 672 newtons. We're interested in the acceleration of gravity on that planet. We're interested in the g on the new planet. So we'll divide by m. And remember, their mass doesn't change. A newton is a kilogram meters per second squared. So kilograms will cancel. And yeah, 12 times 5 is 60, 672 and all that. Yeah, I believe that number, 12 meters per second squared. That's higher than 9.8. On that planet, they would feel gravity pulling on them more. They'd feel heavier. It would probably be more difficult to move around. And I think I'm going to skip this one, the T1, because it's just like the one we just did. Because I want to get into the normal force. We talked a little bit before about the normal force when we saw the example of the thinker. I believe that was in video number 2. And that's the force exerted by a surface perpendicular to the contact. So if a box is sitting on a table, gravity pulls down, but the normal force goes up. And moving forward, I'm going to try to use a lowercase n. That's the way I do normal force, just so we're consistent. Now, this is what's called a free body diagram. You see them all the time in physics. So what we do is, if you can imagine taking that box And if we could crumble it or crush it into it, one little dot, one little point, that's what we do. We crush it to a single point. And we say, okay, what are the only forces? There's a force going up, the normal force on the table, and a force going down, mg, and that's it. We'll see situations where it's not later. Now, if you tilt the table, the normal force still goes up. But notice it's perpendicular to the table, not to the ground. mg never changes. mg always, always, always points straight down the negative y-axis. It never changes. So again, imagine taking that box and crumpling it up like a piece of paper if you could and smashing it all down tight. You'd have mg going down and normal going up, but at an angle. So let's say we have a present sitting on a table. Calculate the weight and the normal force. The weight is pretty easy. That's just mg. 10 times 9.8. The weight is 98 newtons. Now here's where we're really going to start to use Newton's second law. Remember, there's only two choices. The sum of the forces is 0, or the sum of the forces is ma. Now in this case, the box is just sitting there, so the sum of the forces has to be 0. I bring that down. Now let's look at our free body diagram. I should have drawn that first. Normal and mg. Normal is pointing upward in the positive x-axis towards the positive, or y-axis, excuse me. It's pointing straight upward in the positive y-axis. So that means it's positive. mg is pulling downward. It's negative. So sometimes students will say, well, where'd you get that equation? We make it up. We create it based on the free body diagram. Now I want to know the weight and the normal force. So normal equals mg. I think you can see that. If we just move the mg over, we already know the mg is 98. So in practice, or practically, the normal force exactly balances out. The normal force is 98 newtons up. The weight is 98 newtons down. The box will not move. It's not accelerating. We can see that. The sum of the forces is 0. Oops, yep, and I actually have the math right here. Now suppose I'm standing here talking to you, Mr. Saba comes in and he leans on the box, adding an additional 40 newtons, and says, well, calculate the normal force. Again, we're going to do a free body diagram. mg goes down. It always goes down. Normal goes up. But Mr. Saba, you can see his hand. He's leaning on the box there. He's pushing downward with an additional 40 newtons. Well, the box isn't going to move. I mean, he's not pushing on it hard enough that he's going to crush the box or anything. So the box isn't going to move. The sum of the forces is 0. It's at a constant velocity of 0. Now I come over to the free body. Normal is going upward in the positive y-axis. mg is going downward. And so is that 40 newtons from Mr. Saba. So now it says, well, what's the normal force? Well, usually I like to rearrange it, but let's just put the numbers in right now. It's still that 10 kilogram box. That hasn't changed. Minus 40. So let's see the math on the next page. 0 is normal minus mg minus 40. We said the mg is 98. So the normal is 138 newtons. Now that's more. When the box was just sitting there, it was only 98 newtons. When Mr. Saba came in and put his hand on it and pressed down a bit, it spiked. it went up to 138 newtons because the table had to respond. The material of the table had to absorb the extra weight or the extra force from Mr. Saba leaning on the package.